Welcome to the course of Statistics for Data Science and Business Analysis. This course presents the descriptive and inferential statistics, hypothesis testing, and regression analysis. What you'll learn about this course: understand the fundamentals of statistics, learn how to work with different types of data, how to plot different types of data, calculate the measures of central tendency, asymmetry, and variability, calculate correlation and covariance, distinguish and work with different types of distributions, estimate confidence intervals, perform hypothesis testing, make data-driven decisions, understand the mechanics of regression analysis, carry out regression analysis, use and understand dummy variables, understand the concepts needed for data science even with Python and R. Lecture number 1, Understanding the difference between a population and sample.
Alright, before crunching any numbers and making decisions, we should introduce some key definitions. The first step of every statistical analysis you will perform is to determine whether the data you are dealing with is a population or a sample. A population is the collection of all items of interest to our study and is usually denoted with an uppercase N. The numbers we've obtained when using a population are called parameters. A sample is a subset of the population and is denoted with a lowercase n, and the numbers we've obtained when working with a sample are called statistics. Now you know why the field we are studying is called statistics. Let's say we want to make a survey of the job prospects of the students studying in the New York University. What is the population? You can simply walk into New York University and find every student, right? Well, probably that would not be the population of NYU students. The population of interest includes not only the students on campus, but also the ones at home, on exchange, abroad, distance education students, part-time students, even the ones who are enrolled but are still at high school. Though exhaustive, even this list misses someone. Point taken. Populations are hard to define and hard to observe in real life. A sample, however, is much easier to contact. It is less time-consuming and less costly. Time and resources are the main reasons we prefer drawing samples, compared to analyzing an entire population. So let's draw a sample then. As we first wanted to do, we can just go to the NYU campus. Next, let's enter the canteen, because we know it will be full of people. We can then interview 50 of them. Cool. This is a sample. Good job. But what are the chances of these 50 people that provide us answers that are a true representation of the whole university? Pretty slim, right? The sample is neither random nor representative. A random sample is collected when each member of the sample is chosen from the population strictly by chance. We must ensure each member is equally likely to be chosen. Let's go back to our example. We walked into the university canteen and violated both conditions. People were not chosen by chance. They were a group of NYU students who were there for lunch. Most members did not even get the chance to be chosen, as they were not on campus. Thus, we conclude the sample was not random. What about the representativeness of the sample? A representative sample is a subset of the population that accurately reflects the members of the entire population. Our sample was not random, but was it representative? Well, it represented a group of people, but definitely not all students in the university. To be exact, it represented the people who have lunch at the university canteen. Had our survey been about job prospects of NYU students who eat in the university canteen, we would have done well. By now, you must be wondering how to draw a sample that is both random and representative. Well, the safest way would be to get access to the student database and contact individuals in a random manner. However, such surveys are almost impossible to conduct without assistance from the university. We said populations are hard to define and observe. Then, we saw that sampling is difficult. But samples have two big advantages. First, after you have experience, it is not hard to recognize if a sample is representative. And second, statistical tests are designed to work with incomplete data. Thus, making a small mistake while sampling is not always a problem. Don't worry, after completing this course, samples and populations will be a piece of cake for you. Thanks for watching.
Lecture number 2, Understanding the different types of data.
You are probably watching this course because you want to learn the appropriate statistics to perform different tests. However, before we can start testing, we have to get acquainted with the types of variables we usually encounter. Different types of variables require different types of statistical tests. As such, it is key to be able to classify the data you are working with. We can classify data in two main ways, based on its type and on its measurement level. Let's start from the types of data we can have. There is categorical and numerical data. Categorical data describes categories or groups. One example is car brands like Mercedes, BMW, and Audi. They show different categories. Another instance is answers to yes and no questions. If I ask questions like, "Are you currently enrolled in a university?" or "Do you own a car?" Yes and no would be the two groups of answers that can be obtained. This is categorical data. Numerical data, on the other hand, as its name suggests, represents numbers. It is further divided into two subsets, discrete and continuous. Discrete data can usually be counted in a finite manner. A good example would be the number of children that you would want to have. Even if you don't know exactly how many, you are absolutely sure that the value will be an integer, such as 0, 1, 2, or even 10. Another instance is grades on the SAT exam. You may get 1,000, 1,560, 1,570, or 2,400. What is important for a variable to be defined as discrete is that you can imagine each member of the dataset. Knowing that SAT scores range from 600 to 2,400 and 10 points separate all possible scores that can be obtained is key. It's easier to understand discrete data by saying it's the opposite of continuous data. Continuous data is infinite and impossible to count. For instance, your weight can take on every value in some range. Let's dig a bit deeper into this. You get on the scale and the screen shows 150 pounds, or 68.0389 kilograms. But this is just an approximation. If you gain 0.01 pound, the figure on the scale is unlikely to change, but your new weight will be 150.01 pounds, or 68.0434 kilograms. Now think about sweating. Every drop of sweat reduces your weight by the weight of that drop, but a scale is unlikely to capture that change. The process of losing and gaining weight occurs all the time. Your exact weight is a continuous variable. It can take on an infinite amount of values, no matter how many digits there are after the dot. To sum it up, your weight can vary by incomprehensibly small amounts and is continuous, while the number of children you want to have is directly understandable and is discrete. Alright, these were the types of data. In our next lesson, we will explore the levels of measurement.
Lecture number 3, Understanding the Levels of Measurement.
In our previous video, we distinguished between categorical and numerical data. Furthermore, we saw that numerical data can be discrete and continuous. It's time to move on to the other classification, levels of measurement. These can be split into two groups, qualitative and quantitative data. They are very intuitive, so don't worry. Qualitative data can be nominal or ordinal. Nominal values are like the categories we talked about just now. Mercedes, BMW, or Audi, or like the 4 seasons, winter, spring, summer, and autumn. They aren't numbers and cannot be put in any order. Ordinal data, on the other hand, consists of groups and categories, but follows a strict order. Imagine you have been asked to rate your lunch and the options are disgusting, unappetizing, neutral, tasty, and delicious. Although we have words and not numbers, it is obvious that these preferences are ordered from negative to positive. Thus, the data is qualitative ordinal. Okay, so what about quantitative variables? Well, as you may have guessed by now, they are split into two groups, interval and ratio. Intervals and ratios are both represented by numbers, but have one major difference. Ratios have a true zero, and intervals don't. For example, length is a ratio variable. You all know that 0 inches or 0 feet means no length. With temperature, however, we have a different story. It is usually an interval variable. Let me explain. Usually, it is expressed in Celsius or Fahrenheit. They are both interval variables. 0 degrees Celsius or 0 degrees Fahrenheit don't mean anything, as the absolute zero temperature is actually negative 273.15 degrees Celsius or negative 459.67 degrees Fahrenheit. However, we can easily say that 80 degrees Fahrenheit is less than 100 degrees Fahrenheit. In the case of interval variables, the difference is meaningful, but the zero is not. Continuing this temperature example, there is another scale, kelvins. According to it, the absolute minimum temperature is 0 degrees Kelvin. Therefore, if the degrees are stated in kelvins, the variable will be a ratio. So, numbers like 2, 3, 10, 10.5, pi, etc. can be both an interval or a ratio measurement, but you have to be careful with the context you are using them in. Alright, we've quickly gone through the types of data and the measurement levels. Stick around to see the types of graphs that are used on a daily basis when performing statistical analysis.
Lecture number 4, Understanding the Categorical Variables and Visualization Techniques.
Now that we've seen the different types of data and levels of measurement we can have, we are ready to explore different graphs and tables, which will allow us to visually represent the data we are working with. Visualizing data is the most intuitive way to interpret it, so it will be great if we learn how to do that. As you may recall, there are two types of variables, categorical and numerical. In this video, we will focus on categorical variables. The most common ways to visualize them are frequency distribution tables, bar charts, pie charts, and Pareto diagrams. First, let's see what a frequency distribution table looks like. It has two columns, the category itself and the corresponding frequency. Imagine you own a car shop and you sell only German cars. The table below shows the categories of cars, Audi, BMW, and Mercedes, and their frequency, or in plain English, the number of units sold. By organizing your data in this way, you can compare the different brands and see that Audi has been sold the most. No preferences on my side. However, tables aren't much fun, are they? Using the same table, we can construct a bar chart. The vertical axis shows the number of units sold, while each bar represents a different category, indicated on the horizontal axis. In this way, it is much clearer that Audi is the best-selling brand. Okay, let's represent the same data with a pie chart. In order to build one, we need to calculate the percentage of the total of each brand. In statistics, this is known as relative frequency. Naturally, all relative frequencies add up to 100%. Pie charts are especially useful when we not only want to compare items among each other, but also to see their share of the total. This example could be easily transformed into a business example of market share. Market share is so predominantly represented by pie charts that if you search for market share in Google Images, you would get only pie charts. Imagine that the data in our table is representing the sales of Audi, BMW, and Mercedes in a single German city, say Bonn. The chart will show us the market share that each of these brands has. Lastly, we have the Pareto diagram. In fact, a Pareto diagram is nothing more than a special type of bar chart where categories are shown in descending orders of frequency. By frequency, statisticians mean the number of occurrences of each item. As we said earlier, in our example, that's exactly the number of units sold. Let's go back to our frequency distribution table and order the brands by frequency. Now, we can create the bar chart based on our reordered table and voila! We almost have a Pareto diagram. There is one last touch to make it one. A curve on the same graph showing the cumulative frequency. Cumulative frequency is the sum of the relative frequencies. It starts at the frequency of the first brand, then we add the second, the third, and so on until it finishes at 100%. This polygonal line is measured by a different vertical axis on the right of the graph. At the end of its vertices, it shows the sum total of the categories to its left. See how the Pareto diagrams combines the strong sides of the bar and the pie chart. It is easy to compare the data both between categories and as a part of the total. Furthermore, if this was a market share graph, you could easily see the market share of the top 2 or top 5 companies. These are the main ways in which we visually represent categorical data. In our next lecture, we will get acquainted with the most useful graphs and tables for numerical data. Thanks for watching.
Lecture number 5, Understanding the Numerical Variables and Frequency Distribution Table.
Okay, excellent. We already know how to create graphs and tables for categorical variables. In this lesson, we are going to do the same for numerical variables. And given that numerical data is the main focus of this course, we will spend a couple of lessons on this topic. Now, whenever we want to plot data, it is best to first order it in a table. So, as we did with categorical variables, let's start by creating a frequency distribution table. Here's a list of 20 different numbers. If we arrange them in a frequency table like the one we use for categorical variables, we would obtain a table with 20 rows, each of them representing one number of a corresponding frequency of 1, as each number occurs exactly one time. This table would be impractical for any analysis, right? Well, when we deal with numerical variables, it makes much more sense to group the data into intervals and then find the corresponding frequencies. In this way, we make a summary of our data that allows for a meaningful visual representation. How do we choose these intervals? Generally, statisticians prefer working with the groups of data that contain 5 to 20 intervals. This way, the summary can be useful. However, this varies from case to case, and the correct choice of intervals largely depends on the amount of data we are working with. In our example, we will divide the data into 5 intervals of equal length. The simple formula that we use is as follows. The interval width is equal to the largest number minus the smallest number, divided by the number of desired intervals. In our case, the length of the interval should be 100 minus 1, divided by 5. The result is 19.8. Now we want to round this number up in order to reach a neater representation. Therefore, our intervals will be as follows: 1 to 21, 21 to 41, 41 to 61, 61 to 81, and 81 to 101. Each interval has a width of 20. Okay, let's try to construct the frequency distribution table. We'll have to work with 2 components, intervals and frequency. As we can see from the table, there are 2 numbers in the first interval, 4 in the second, 3 in the third, 6 in the fourth, and 5 in the fifth interval. For many analysis, it is useful to calculate the relative frequency of the data points. As we said in a previous video, the relative frequency is the frequency of a given interval as a part of the total. Let's add another column to our table and name it relative frequency. So, the interval from 1 to 20 has an absolute frequency of 2, but a relative frequency of 2 divided by the total of 20 numbers, which gives us 10%, and so on as we fill the table. Alright, this is how we calculate relative frequencies. Now that we have summarized the raw data, we can start plotting it.
Lecture number 6, Understanding the Histogram.
The most common graph used to represent numerical data is the histogram. First, we'll learn how to create it, and then we'll provide a description of the way the data is represented. We are going to use the frequency distribution table from our previous example to help us out. Here it is. As you can see, it looks like a bar chart, but actually conveys very different information. As in the bar chart, the vertical axis is the numerical type and shows the absolute frequency. This time though, the horizontal axis is numerical too. To use the other classification we already know, it is quantitative data of the interval type. Alright, so each bar has width equal to the interval and height equal to the frequency. Notice how the different bars are touching. This is to show that there is continuation between the intervals. Each interval ends where the next one starts. In the bar chart, however, different bars represented different categories, so the bars were completely separate. Okay, sometimes it is useful to plot the intervals against the relative, rather than the absolute frequency. As you can see, the histogram looks the same visually, but gives different information to the audience. Remember, relative frequency is made up of percentages. There is one last thing to note here. We may create a histogram with unequal intervals. An example is designing age groups. You've likely completed some survey where you were asked about your age, and the possible answers were 18 to 25, then 25 to 30, 30 to 35, and so on until 60 plus. Clearly, the interval widths vary and reflect different focus groups for the experiment at hand. An explanation for this choice may be, young adults under 25 cannot afford the product, while adults over 60 have no interest in the product. In any case, you should be quite experienced to accurately design and interpret such groups. It is highly recommended that you stick with the equal width intervals until you gain enough experience. Okay, great! This is how we can build a histogram in order to represent numerical data. Stay tuned for our next lesson, where we will see graphs that allow us to observe the relationship between variables.
Lecture number 7, Understanding the Cross Tables and Scatter Plot.
So far, we covered graphs that represent only one variable. But how do we represent relationships between two variables? In this video, we'll explore cross tables and scatter plots. Once again, we have a division between categorical and numerical variables. Let's start with categorical variables. The most common way to represent them is using cross tables, or as some statisticians call them, contingency tables. Imagine you are an investment manager and you manage stocks, bonds, and real estate investments for 3 different investors. Each of them has a different idea of risk, and hence their money is allocated in a different way among the 3 asset classes. A cross table representing all the data looks in the following way. You can clearly see the rows showing the different type of investment that's been made, and the columns with each investor's allocation. It is good practice to calculate the totals of each row and column, as it is often useful in further analysis. Notice that the subtotals of the rows give us total investment in stocks, bonds, and real estate. On the other hand, the subtotals of the columns gives us the holdings of each investor. Once we have created a cross table, we can proceed to visualizing the data onto a plane. A very useful chart in such cases is a variation of the bar chart called the side-by-side bar chart. It represents the holdings of each investor in the different types of assets. Stocks are in green, bonds are in red, and real estate is in blue. The name of this type of chart comes from the fact that for each investor, the categories of assets are represented side by side. In this way, we can easily compare asset holdings for a specific investor or among investors. Easy, right? All graphs are very easy to create and read once you have identified the type of data you are dealing with and decided on the best way to visualize it. Finally, we would like to conclude with a very important graph, the scatter plot. This is used when representing 2 numerical sets of data. For this example, we have gathered the reading and writing SAT scores of 100 individuals. Let me first show you the graph before analyzing it. Alright, first, SAT scores are component range from 200 to 800 points. That is why our data is bounded within the range of 200 to 800. Second, our vertical axis shows the writing scores, while the horizontal axis contains the reading scores. Third, there are 100 students, and their results correspond to a specific point on the graph. Each point gives us information about a particular student's performance. For example, this is Jane. She scored 300 on writing, but 550 on the reading part. Scatter plots usually represent lots and lots of observations. When interpreting a scatter plot, A statistician is not expected to look into single data points. He would be much more interested in getting the main idea of how the data is distributed. Okay, the first thing we see is that there is an obvious uptrend. This is because lower writing scores are usually obtained by students with lower reading scores, and higher writing scores have been achieved by students with higher reading scores. This is logical, right? Students are more likely to do well on both because the two tasks are closely related. Second, we notice a concentration of students in the middle of the graph with scores in the region of 450 to 550 on both reading and writing. Remember that we said that scores could be anywhere between 200 and 800? Well, 500 is the average score one can get, so it makes sense that a lot of people fall into that area. Third, there is a group of people with both very high writing and reading scores. The exceptional students tend to be excellent at both components. This is less true for bad students, as their performance tends to deviate when performing different tasks. Finally, we have Jane from a minute ago. She is far away from every observation, as she scored above average on reading but poorly on writing. This observation is called an outlier, as it goes against the logic of the whole dataset. We will learn more about outliers and how to treat them in our analysis later on in this course. So, we have gone through the basics. We have covered populations, samples, types of variables, graphs, and tables. It is time for us to dive into the heart of descriptive statistics, measurements of central tendency and variability. Thanks for watching.
Lecture number 8, Understanding the Mean, Median and Mode.
This lesson will introduce you to the three measures of central tendency. Don't be scared by the terminology. We are talking about mean, median, and mode. Even if you are familiar with these terms, please stick around as we will explore their upsides and shortfalls. Ready? Let's go. The first measure we will study is the mean, also known as the simple average. It is denoted by the Greek letter mu for a population and x bar for a sample. These notions will come in handy in the next section. We can find the mean of a dataset by adding up all of its components and then dividing them by the number of components contained in the dataset. The mean is the most common measure of central tendency, but it has a huge downside. It is easily affected by outliers. Let's compare these two datasets. These are the prices of pizza at 11 different locations in New York City and 10 different locations in LA. Let's calculate the means of the two datasets using the formula. For the mean in NYC, we get $11, whereas for LA, just 5.5. On average, pizza in New York can't be twice as expensive as in LA, right? Correct. The problem is that in our sample, we have included one posh place in New York where they charge $66 for pizza, and this doubled the mean. What we should take away from this example is that the mean is not enough to make definite conclusions. So, how can we protect ourselves from this issue? You guessed it, we can calculate the second measure, the median. The median is basically the middle number in an ordered dataset. Let's see how it works for our example. In order to calculate the median, we have to order our dataset in ascending order. The median of the dataset is the number at position n plus 1 divided by 2 in the ordered list, where n is the number of observations. Therefore, the median for NYC is at the 6th position, or $6. Much closer to the observed prices than the mean of $11, right? What about LA? We have just 10 observations in LA. According to our formula, the median is at position 5.5. In cases like this, the median is the simple average of the numbers at positions 5 and 6. Therefore, the median of LA prices is $5.5. Okay, we have seen that the median is not affected by extreme prices, which is good when we have posh New York restaurants in a street pizza sample. But we still don't get the full picture. Are the majority of restaurants low cost or average? We must introduce another measure, the mode. The mode is the value that occurs most often. It can be used for numerical and categorical data, but we will stick to our numerical example. After counting the frequencies of each value, we find that the mode of New York pizza prices is $3. Now that's interesting. The most common price of pizza in NYC is just $3, but the mean and median led us to believe it was much more expensive. Okay, let's do the same and find the mode of LA pizza prices. Each price appears only once. How do we find the mode then? Well, we say that there is no mode. But can I say that there are 10 modes, you may ask? Sure, you can, but it will be meaningless with 10 observations, and an experienced statistician would never do that. In general, you often have multiple modes. Usually, 2 or 3 modes are tolerable, but more than that would defeat the purpose of finding a mode. There is one last question that we haven't answered. Which measure is best? The NYC and LA example shows us that measures of central tendency should be used together rather than independently. Therefore, there is no best, but using only one is definitely the worst. Alright, now you know about the mean, median, and mode. In our next video, we will use that knowledge to talk about skewness. Stay tuned and thanks for watching.
Lecture number 9, Understanding the Skewness.
After exploring the measures of central tendency, let's move on to the measures of asymmetry. The most commonly used tool to measure asymmetry is skewness. This is the formula to calculate it. Almost always, you will use software that performs the calculation for you. So in this lesson, we will not get into the computation, but rather the meaning of skewness. So, skewness indicates whether the observations in a dataset are concentrated on one side. Skewness can be confusing at the beginning, so an example is in place. Remember frequency distribution tables from previous lectures? Here we have 3 datasets and their respective frequency distributions. We have also calculated the means, medians, and modes. The first dataset has a mean of 2.79 and a median of 2, hence the mean is bigger than the median. We say that this is a positive or right skew. From the graph, you can clearly see that the data points are concentrated on the left side. Note the direction of the skew is counterintuitive. It does not depend on which side the line is leading to, but rather to which side its tail is leading to. So, right skewness means that the outliers are to the right. It is interesting to see the measures of central tendency incorporated in the graph. When we have the right skewness, the mean is bigger than the median, and the mode is the value with the highest visual representation. In the second graph, we have plotted a dataset that has an equal mean, median, and mode. The frequency of occurrence is completely symmetrical, and we call this a zero or no skew. Most often, you will hear people say that the distribution is symmetrical. For the third dataset, we have a mean of 4.9, a median of 5, and a mode of 6. As the mean is lower than the median, we say that there is a negative or left skew. Once again, the highest point is defined by the mode. Why is it called a left skew again? That's right, because the outliers are to the left. Alright, so why is skewness important? Skewness tells us a lot about where the data is situated. As we mentioned in our previous lesson, the mean, median, and mode should be used together to get a good understanding of the dataset. Measures of asymmetry like skewness are the link between central tendency measures and probability theory, which ultimately allows us to get a more complete understanding of the data we are working with.
Lecture number 10, Understanding the Variance.
Next on our to-do list are the measures of variability. There are many ways to quantify variability. However, we will focus on the most common ones: variance, standard deviation, and coefficient of variation. In the field of statistics, we will typically use different formulas when working out the population data and sample data. Let's think about this for a bit. When you have the whole population, each data point is known, so you are 100% sure of the measures you are calculating. When you take a sample of this population and you compute a sample statistic, it is interpreted as an approximation of the population parameter. Moreover, if you extract 10 different samples from the same population, you will get 10 different measures. Statisticians have solved the problem by adjusting the algebraic formulas for many statistics to reflect the issue. Therefore, we will explore both population and sample formulas, as they are both used. You must be asking yourself why there are unique formulas for the mean, median, and mode. Well, actually, the sample mean is the average of the sample data points, while the population mean is the average of the population data points. Technically, there are two different formulas, but they are computed in the same way. Okay, now, after this short clarification, it's time to get onto variance. Variance measures the dispersion of a set of data points around their mean value. Population variance, denoted by sigma squared, is equal to the sum of squared differences between the observed values and the population mean, divided by the total number of observations. Sample variance, on the other hand, is denoted by s squared and is equal to the sum of squared differences between observed sample values and the sample mean, divided by the number of sample observations minus 1. Alright, when you are getting acquainted with statistics, it is hard to grasp everything right away. Therefore, let's stop for a second to examine the formula for the population and try to clarify its meaning. The main part of the formula is its numerator, so that's what we want to comprehend. The sum of the differences between the observations and the mean squared. So, the closer the number to the mean, the lower the result we will obtain, right? And the further away from the mean it lies, the larger the difference. Easy. But why do we elevate to the second degree? Squaring the differences has two main purposes. First, by squaring the numbers, we always get non-negative computations. Without going too deep into the mathematics of it, it is intuitive that dispersion cannot be negative. Dispersion is about distance, and distance cannot be negative. If, on the other hand, we calculate the difference and do not elevate to the second degree, we would obtain both positive and negative values that, when summed, would cancel out, leaving us with no information about the dispersion. Second, squaring amplifies the effect of large differences. For example, if the mean is 0 and you have an observation of 100, the squared spread is 10,000. Alright, enough dry theory. It's time for a practical example. We have a population of 5 observations. 1, 2, 3, 4, and 5. Let's find its variance. We start by calculating the mean. 1 plus 2 plus 3 plus 4 plus 5 divided by 5 equals 3. Then we apply the formula we just saw. 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared. All of these components have to be divided by 5. When we do the math, we get 2. So, the population variance of the dataset is 2. But what about sample variance? This would only be suitable if we were told that these 5 observations were a sample drawn from a population. So let's imagine that's the case. The sample mean is once again 3. The numerator is the same, but the denominator is going to be 4 instead of 5, giving us a sample variance of 2.5. To conclude the variance topic, we should interpret the result. Why is the sample variance bigger than the population variance? In the first case, we knew the population, that is, we had all the data and we calculated the variance. In the second case, we were told that 1, 2, 3, 4, and 5 was a sample drawn from a bigger population. Now imagine the population of this sample were 1, 1, 1, 2, 3, 4, 5, 5, and 5. Clearly, the numbers are the same, but there is a concentration about the two extremes of the dataset, 1 and 5. The variance of this population is 2.96. So, our sample variance has rightfully corrected upwards in order to reflect the higher potential variability. This is the reason why there are different formulas for sample and population data. This was a very important lesson, so please make sure you have understood it well. You can reinforce what you have learned here by doing the exercise available in the course resources section. Remember, the subject of statistics is only understood when practiced.
Lecture number 11. Understanding the standard deviation and coefficient of variation.
While variance is a common measure of data dispersion, in most cases the figure you will obtain is pretty large and hard to compare as the unit of measurement is squared. The easy fix is to calculate its square root and obtain a statistic known as standard deviation. In most analyses you perform, standard deviation will be much more meaningful than variance. As we saw in the previous lecture, there are different measures for the population and sample variance. Consequently, there is also population and sample standard deviation. The formulas are the square root of the population variance and the square root of the sample variance respectively. I believe there is no need for an example of the calculation, right? If you have a calculator in your hands, you'll be able to do the job. Alright. The other measure we still have to introduce is the coefficient of variation. It is equal to the standard deviation divided by the mean. Another name for the term is relative standard deviation. This is an easy way to remember its formula. It is simply the standard deviation relative to the mean. As you probably guessed, there is a population and sample formula once again. So, standard deviation is the most common measure of variability for a single dataset. But why do we need yet another measure such as the coefficient of variation? Well, comparing the standard deviations of two different datasets is meaningless, but comparing coefficients of variation is not. Aristotle once said, "Tell me, I'll forget. Show me, I'll remember. Involve me, I'll understand." To make sure you remember, here's an example of a comparison between standard deviations. Let's take the prices of pizza at 10 different places in New York. They range from $1 to $11. Now, imagine that you only have Mexican pesos, and to you the prices look more like 18.81 pesos to 206.91 pesos, given the exchange rate of 18.81 pesos for $1. Let's combine our knowledge so far and find the standard deviations and coefficients of variation of these two datasets. First, we have to see if this is a sample or a population. Are there only 11 restaurants in New York? Of course not. This is obviously a sample drawn from all the restaurants in the city. Then we have to use the formulas for sample measures of variability. Second, we have to find the mean. The mean in dollars is equal to 5.5, and the mean in pesos is 103.46. The third step of the process is finding the sample variance. Following the formula that we showed earlier, we can obtain $10.72 squared and 3,793.69 pesos squared. The respective sample standard deviations are $3.27 and 61.59 pesos. Let's make a couple of observations. First, variance gives results in squared units, while standard deviation in original units. This is the main reasons why professionals prefer to use standard deviation as the main measure of variability. It is directly interpretable. Squared dollars means nothing, even in the field of statistics. Second, we got standard deviations of 3.27 and 61.59 for the same pizza at the same 11 restaurants in New York City. Seems wrong, right? Don't worry, it is time to use our last tool, the coefficient of variation. Dividing the standard deviations by the respective means, we get the two coefficients of variation. The result is the same, 0.60. Notice that it is not dollars, pesos, dollars squared, or pesos squared. It is just 0.60. This shows us the great advantage that the coefficient of variation gives us. Now, we can confidently say that the two datasets have the same variability, which is what we expected beforehand. Let's recap what we have learned so far. There are three main measures of variability: variance, standard deviation, and coefficient of variation. You should feel confident using all of them, as we are getting closer to more complex statistical topics. And remember Aristotle's advice: involve me, I'll understand. So, please don't forget to get involved with the exercises.
Lecture number 12, Understanding the Covariance.
Alright, excellent. We've covered all univariate measures. Now, it is time to see measures that are used when we work with more than one variable. In the next 2 lessons, we'll explore measures that can help us explore the relationship between variables. Our focus will be on covariance and the linear correlation coefficient. Let's zoom out a bit and think of an example that is very easy to understand and will help us grasp the nature of the relationship between 2 variables a bit better. Think about real estate. Which is one of the main factors that determine house prices? Their size, right? Typically, larger houses are more expensive, as people like having extra space. The table that you can see here shows us data about several houses. On the left side, we can see the size of each house, and on the right, we have the price at which it's been listed in a local newspaper. We can present these data points in a scatter plot. The x-axis will show a house's size, and the y-axis will provide information about its price. We can certainly notice a pattern. There is a clear relationship between these variables. We say that 2 variables are correlated, and the main statistic to measure this correlation is called covariance. Unlike variance, covariance may be positive, equal to 0, or negative. To understand the concept better, I would like to show you the formulas that allows us to calculate the covariance between 2 variables. It is formulas with an S, because once again there is a sample and population formula. Here they are. Since this is obviously sample data, we should use the sample covariance formula. Let's apply it in practice for the example that we saw earlier. X will be the house size, and Y stands for house prices. First, we need to calculate the mean size and the mean price. Okay, done. Now, let's calculate the denominator of the covariance function. Starting with the first house, I'll multiply the difference between its size and the average house size by the difference between the price of the same house and the average house price. Once we're ready, we have to perform this calculation for all the houses that we have in the table, and then sum the numbers we've obtained. See? Great! Our sample size is 5. Now we have to divide the sum above by the sample size minus 1. The result is the covariance. It gives us a sense of direction in which the 2 variables are moving. If they go in the same direction, the covariance will have a positive sign, while if they move in the opposite directions, the covariance will have a negative sign. Finally, if their movements are independent, the covariance between the house size and its price will be equal to 0. There is just one tiny problem with covariance though. It could be a number like 5 or 50, but it can also be something like 0.0023456 or even over 30 million as in our example. Totally different values. How could one interpret such numbers? Proceed to the next lecture to find out how the correlation coefficient can help us with this issue. Thanks for watching.
Lecture number 13, Understanding the Correlation.
Correlation adjusts covariance so that the relationship between the 2 variables becomes easy and intuitive to interpret. The formulas for the correlation coefficient are the covariance divided by the product of the standard deviations of the 2 variables. This is either sample or population, depending on the data you are working with. We already have the standard deviations of the 2 datasets. Now we'll use the formula in order to find the sample correlation coefficient. Mathematically, there is no way to obtain a correlation value greater than 1 or less than -1. Remember the coefficient of variation we talked about a couple lessons ago? Well, this concept is similar. We manipulated the strange covariance value in order to get something intuitive. Let's examine it for a bit. We got a sample correlation coefficient of 0.87, So for each foot increase in size of a house, its price rises by $870. Okay, what about the general case? A correlation of 1, also known as perfect positive correlation, means that the entire variability of one variable is explained by the other variable. In our case, this means that for every additional square foot of size, we would expect an increase of, let's say, $1,000 in the house price. For instance, 5 additional square feet will lead to a price increase of $5,000. 10 additional square feet would lead to a price increase of $10,000, and so on. In that case, the observations in our plot will form a straight line, as the correlation between size and price has to be perfect. It would mean that the size is the only variable that determines a house's price, and that we can easily calculate a house's price if we know its size. Before we continue, we must note that the correlation between two variables x and y is the same as the correlation between y and x. The formula is completely symmetrical with respect to both variables. Therefore, we must expect that an increase in price of $1,000 will also mean that the size must be 1 square foot larger. However, logically we know that size determines price. On average, the bigger house you build, the more expensive it will be. This relationship only goes this way. Once a house is built, if for some reason it becomes more expensive, its size doesn't increase, although there is a positive correlation. This leads us to causality. It is very important for any analyst or researcher to understand the direction of causal relationships. In the house business, size causes the price, and not vice versa. We will explore this topic in much more detail in the regression analysis section later on. For now, it is only needed that you realize that correlation does not imply causation. Okay, a correlation of 0 between two variables means that they are absolutely independent from each other. We would expect a correlation of 0 between the price of coffee in Brazil and the price of houses in London, right? The two variables don't have anything in common. Finally, we can have negative correlation coefficient. It can be perfect negative correlation of -1, or much more likely an imperfect negative correlation of a value between -1 and 0. Think of the following businesses: a company producing ice cream and a company selling umbrellas. Ice cream tends to be sold a lot more when the weather is very good, and people buy umbrellas when it's rainy. Obviously, there is a negative correlation between the two, and hence when one of the companies makes more money, the other won't. Okay, very good. With this example, we conclude the section on descriptive statistics. In the next lesson, you will see a real-life database example that applies all the knowledge you acquired in this section. You definitely don't want to miss it.
Lecture number 14, Understanding the Practical Example.
Finally, it's time for the practical example we've been talking about. In this lesson, we will see an actual database of a real estate company operating in California. Alright, we're interested in the statistical properties of the data. That is why we have reordered the database and cherry-picked variable, then imported these in a spreadsheet. The labels of the columns have been made friendly, even for those of you who have no experience with real estate. Finally, we have altered the names of the customers for confidentiality reasons. Okay, the company is launching a marketing campaign, but it wants to target its audience properly. The management suspects, after some short analysis, marketing results can be improved without the need of investing additional resources. We are the data analysts who are going to crunch some numbers and identify which groups of people are most likely to buy our product. Once we have done so, we will instruct the marketing team to focus its efforts on these groups. The first thing we have to do when we analyze data is get acquainted with the table. It illustrates the sales of real estate property for a specific company. Let's call it 365 Data Science Real Estate California. Hopefully, no one else thought of that name. Second, the table has two parts, left and right. On the left-hand side, we have product information. On the right-hand side, we have customer information. You can easily spot all products are listed, but customer information is only available for some products. This is because we input information about a customer once the deal is done. Logically, only sold items are associated with a buyer. Let's see what a row looks like. This should clear up the logic of the table for you. Nora Lynch, with a customer ID C0004, was 56 years old when she bought apartment 43 in Building 1 to live there. She paid $377,313 for an area of 1,160 square feet in June 2004. Nora is from California, felt very satisfied with the deal, and did not get a mortgage for the purchase. She found out about our product through our website. Okay, now that that's out of the way, we need to dig deeper into these variables. We will identify types of data and levels of measurement for some of them. This is a crucial step, as we cannot analyze the data if we don't understand its type. Let's start from the first column, ID. ID is a value we assign to each item that lets us differentiate between products. It may look numerical to you, but it is categorical. That's counterintuitive the first time, so let's clarify it. What if we use names like John, John 2, John 3, and so on until John N? The meaning would not change. ID variables are like names we assign to different products. However, it is much easier to use numbers, as unlike names, we have an infinite number of numbers. A simple way to check if a variable is numerical or categorical is to interpret its mean. Think about it. The mean ID number shows nothing. Now oppose this to the mean price. The mean price is a valuable piece of information. Okay, the bottom line is ID is a categorical variable. What about its level of measurement? Well, it is qualitative, nominal. Clear? Clear. The next variable we must examine is age. Age is rather interesting. The level of measurement is quantitative ratio. A rule used for verifying ratios is asking the question, is there a true 0 point? Well, for age, when you are born, you are exactly 0 years old. That's the true 0 point, so we are safe. However, what's intriguing is whether age is discrete or continuous. It may be both. In this case, we can only see age as a whole number, therefore it is discrete. However, similar to weight, a variable we discussed earlier in this course, age is a continuous variable. When I am recording this, the Statue of Liberty is 131 years old, but I may get more specific by saying it is 131 years and 11 months old, or its age is 131.92. If I add days, minutes, and seconds, I'll get 131,9,412. You get the point. When dealing with age, you decide its type, depending on your work at hand. The next variable we have is age interval. This is yet another way to represent age. Once again, it is continuous or discrete as we are talking about the same variable. This time though, the level of measurement is ordinal instead of a ratio. The age groups represent different categories ordered, but are not numerical. This shows that the same variable can have different levels of measurement within the same database. Alright, let's move on. In most corporate analysis, price is central. No matter the dataset, it is always a numerical variable that, like age, may be discrete or continuous, depending on your needs. If you are interested, banks and corporations treat it as continuous, and so will we. The level of measurement here is ratio. The next variable we want to look into is gender. It is of categorical type, and its level of measurement is nominal. It is similar to the yes-no questions discussed in a previous lesson. Such variables are called binary, as there are only two possibilities. Finally, let's check out the location. We will discuss state in more detail and leave country for homework. The state variable refers to sales in the USA only. Note that only if the country input is USA would we have a value for state. State is a categorical variable like ID we talked about earlier. You can label the US states from 1 to 50 and use numbers instead. Either way, the variable is categorical and its level of measurement is nominal. Okay, excellent. We've categorized the variables we will use in this video. This spreadsheet is available for you in the Resources section. With the exercises we've prepared on this database, you can practice the entire section about descriptive statistics. Alright, back to our problem at hand. We must identify the groups of people who buy the most of our product. Let's start with gender. Before we can plot the data, we must create the frequency distribution table. In the course notes, you can see how that's done in Excel. However, in this video, I'll skip this step and get to the frequency distribution table. Now, we have three possibilities for gender: male, female, or a cell where gender is not available. Since some properties were purchased by companies, they have no gender. We have to include them in the analysis or explain why we omitted it in the report. Gender is categorical. We said that a good way to represent it in practice is with a pie chart. Okay, we can clearly see most clients are male. However, this information is biased, as the customers in this database are the people who signed the contract. It is likely a family bought the apartment, but our data shows us only the person who signed the contract. Such variables are interesting to see, but it is not a good idea to include them in the data-driven decisions we make. Okay, let's carry on with location. What chart would be useful to show this? State is a categorical variable. We may use a bar chart or a pie chart. However, I prefer the Pareto diagram as it gives additional information. From the graph, you can immediately see most clients are from California. A possible scenario is to invest in marketing for the top 75% of the locations. This will mean we can focus on California and Nevada alone. Next, we want to see age. First, we have to note that age represents the age of the buyer when the deal was sealed. The formula used is the year of the deal minus the year of the birth of the buyer. We are doing this because we want to see the age at which customers buy our product. Their current age is irrelevant. Real estate is something people rarely buy more than once in their life, so age will probably be a central variable in our analysis. Let's first plot the frequency distribution of age. This is done by creating a histogram with an interval length of 1. Now, we can move on to the age interval representation. The options are 18 to 25, 26 to 35, 36 to 45, 56 to 65, and 65 plus. Most of the data falls between 25 and 60 years, which is evident from the frequency distribution graph. Therefore, our intervals are a good fit of the data. Let's build a new histogram based on them. Done. This representation is much neater, isn't it? We can clearly see 36 to 45 is the age at which most people purchase a real estate property. It is evident that customers from 26 to 65 years old account for 71% of our observations. But we are better than this. We can calculate more statistics to get an improved idea, can't we? Let's do it. The mean, median, and mode are the place where we usually start. The mean age is 46.15 years, the median age is 45 years, and the mode is 48 years. Alright, the mean and median are close, so we have few outliers. As you may recall, the mean is affected by them, while the median is not. When the mean is higher than the median, we have a positive or right skew. This is confirmed by our histogram. Now is the time to remind you that skewness shows to which side is the longer tail, not where the data is concentrated. Now, for the mode, we have 48 years. You can see that from the frequency distribution graph, but not from the histogram. The histogram bundles data together, which is good when we want to see the main trend, but some information like the mode is lost. Finally, we should inspect the variability of age. Before we can do so, we have to see if this is sample or population data. The company data is the population of all people who are our customers. However, our research aims to help the marketing department identify future customers. Therefore, our dataset is a sample drawn from all the people who will eventually buy property from our company. Henceforth, we will use sample formulas. let's compute both the variance and the standard deviation. The former is measured in squared years and the latter in years. So I suggest we stick with the standard deviation then, shall we? The result is around 13 years. This shows us how dispersed the data is. What inferences can we make from this result? Well, that's the topic of the next section, so we will have to halt here. As you may have guessed, our final stop is relationship between variables. Let's see if age determines how expensive an apartment that customers buy. Maybe younger people have less funds, so they buy cheaper apartments. We don't know. The data will tell us. First things first, let's plot the data. Both variables are numerical, so we must use a scatter plot. Here it is. It is dispersed, and there isn't an obvious trend. Let's confirm this observation by calculating the covariance of the two variables. We get this enormous value that doesn't tell us much, so it's suitable to standardize it by using the correlation coefficient. The value we get is minus 0.17. Much better. This correlation is low. A common practice is to disregard correlations that are below 0.2. Alright, so real estate expenditure is not related to age. From a previous lesson, we know price and size are much more likely to be correlated, right? You have all the tools needed to check this through the exercise after this lesson. So we've exhausted our statistical knowledge. What can we tell the marketing team after this short analysis? Well, we got several insights. First, males are more likely to sign contracts and are potentially a better audience for our ads. However, we have no information about their marital status. This observation is unclear. Second, 68% of our sales in the US come from California, with Nevada, Oregon, Arizona, and Colorado following behind to form 93% of the US customer base. Third, 71% of sales were made with customers aged between 26 and 55 years old, with a mean of 46 years of age and a standard deviation of 13 years. The distribution is right skewed, so we expect younger people to buy more property than older people. Finally, there is no relationship between the age of a customer and the price they will pay. Alright, that was our practical example. We learned a lot about this business, but we could not get amazing insights. In the following sections, we will learn about confidence intervals and hypothesis testing. This knowledge will provide us with the tools we need to make predictions about the future and make data-driven decisions. Oh, and one more thing. If you like the course so far, please leave us a review. It helps a lot. Thanks for practicing and thanks for watching.